Okay, so for the following circuit here, we have to solve for IT for when t is greater than 0, and then we're told that switch 1 is closed when t is 0, and then 4 seconds later switch 2 is closed. So there's actually going to be two formulas to represent IT. So let's start for when t is less than 0. Okay, so when t is less than 0, the current is actually 0, because notice this switch is open, so the current passing through it is 0, and this switch is open, so the current passing through it here is 0. So that means the current passing through here is also 0. So now let's focus on when t is greater than or equal to 0 but less than 4. This is how the circuit's going to look like. This wire is obviously going to be closed. Or sorry, switch is going to be closed. And since this one is open, we're going to ignore it. So our circuit looks like this. Okay, so for our I value, what's it going to be? The second when t is equal to 0. Well, it's also so our I value when t is 0 is also going to be 0, because when it was less than 0, our I value was 0, and the second t is equal to 0, our current can't just change instantaneously across our inductor, so it has to also be 0. Okay, so now this is what we're going to do now. We have to we're going to use this formula to solve for IT for when it's between 0 and 4. So it's I infinity plus plus I of 0 minus I of infinity times e to the power of t over the time constant. So this formula is used either when you have no circuit when one of your switches is off, or if there's like a source when your switch is on or off. So in this case, when our switch was on, there was a source here, and when our switch was off, there was no current, like there was literally no circuit involved. Okay, so you use this formula when the switch is on or off, but there's still some kind of source involved, whether this is a voltage source or current source, or when it's on and there's literally no circuit involved, or when it's off and there's literally no circuit involved, then this is when you use this formula. So we already know what I0 is. It's 0. We need to find what I infinity is. So let's try and find the voltage at this inductor. It's going to be equal to the inductance times the change in current over the change in time. Okay, but this is what we're going to do. To solve for I infinity, how are we going to do this? Because this circuit is confined from 0 to 4. So what we're going to do is we're going to pretend the circuit is not confined to 4, but confined to infinity. And now, since it's confined to infinity, dt will be infinity. So that means our voltage will be 0. So we can replace this with a short circuit. And now we can solve for I infinity. Okay, so we can do a mesh of I. So it'll be 40 equals I times 6 plus 4. So I will be 4. Okay, and that's I infinity. Now our time constant is what's left. So our time constant is equal to the inductance value over the resistance equivalent in between that inductance value. So our inductance value was 5, and if you find a resistance equivalent between here, obviously we'll just close this. So because it's a voltage source that's independent, so our resistance equivalent will be the sum of these two voltages. So 6 plus 4, which is 10, which is 1 over 2. So now our IT value will be I infinity, which is 4, plus I of 0, which is 0, minus 4, times e to the power of t over 1 over 2. So IT equals 4 minus 4 e minus 2t amps. And this is oh yeah, and then switch this infinity back to 4, okay? This is 4 is less than t, but greater than or equal to 0, okay? So this formula is confined to this, hold on. It's confined to this circuit, okay? So this formula is only confined to this circuit because the second t is 4, we add this portion, we turn on this wire, sorry, turn on this switch, and that switch causes this portion of the circuit to start getting involved. Okay, so this is 40 volts, this is 10 volts, and this is 2 ohms. And this is to represent when t is greater than or equal to 4. And this is 5 Henry here. Now, to find a formula for when t is greater than or equal to 4, it's going to be I of t equals I infinity. And since we're starting off our last circuit, which was when, this portion wasn't involved, it's not going to be I of 0, it's going to be I of 4, because that's where we start off from our last circuit, minus I infinity times e to the power of t minus 4 over the time constant. So it's not just minus t over the time constant, it's minus t over 4, because again, we're starting off from our last circuit, so we have to subtract 4 seconds to get it to 0. Okay? So first, things first, we have to solve for what I of 4 will be. So how are we going to solve this I of 4? Well, we're going to actually use this equation. So we're going to set t to be, we're going to set this to be 4, t to be 4, and it's going to be 4 minus 4 e to the power of 2 times 4. And that gives me the following. Give me a sec. It gives me 3.998. Okay? Hold on, let me just quickly double check again, just in case. And yeah, I'm right. Okay. So that's I4. And you may be asking, why are we using this formula when this when it's confined from 4 is less than, when t is less than 4 and greater than or equal to 0. It didn't say t is equal to 4, but just it's going to be just less than 4. Well, so the reason we're using this formula is because we know that the current can change instantaneously the second the second switch is on. So, for example, when t is 3.9999999 and repeating, okay, we can plug that value in, and the second t is 4. The current we get, from here, 3.99 and so on, is roughly going to be equal to the current when t is 4. Okay, so we might as well just set this to 4. So I hope I was able to explain it well, but just know that we're allowed to use the previous formula just to figure out I4. Now we just have to figure out I infinity. So since we're taking t to be greater than or equal to 4, we can solve for I infinity. So for the voltage at this inductor, it's going to be the inductance value times the change in current over the change in time. Time goes to infinity, so the voltage is 0. So we can short circuit here. And now we can do a nodal analysis. So let's have a current here, I1, current here, I2. So node V will be I1 plus I2 plus I. So it will be V minus 40 all over 4 plus V minus 10 all over 2 plus V minus 0 all over 6. And this is going to be our I value that we're going to work with. So let's add up all our V's. So V over 40 plus V over 2 plus V over 6 is 0.916667 V. Then we have minus 40 over 4 plus minus 10 over 2, which is minus 15. So V will be 15 over 0.916667. So that's 16.363. And then our I value, which will give us our I infinity value, will be V over 6. So 16.363 over 6, that's 2.727 amps. Okay, next we have to find our time constant. Our time constant will be equal to the inductance value over the resistance equivalent. Inductance value is 5. Now going back to this circuit, we just have we find an resistance equivalent from between here. So we turn off all independent sources. So these two are in parallel. So 1 over 4 plus 1 over 2 to the power of minus 1. So that's 1.333 plus 6. So 7.333. So that's the resistance equivalent. And this gives me 0.681818 seconds. And now we have enough for information. So I of t equals I infinity, which is 2.727 plus I of 4. Oh no, I think I erased what I of 4 was. So I have to quickly get that back. I think it was 3.998. Yeah, it was that. Minus 2.727 e to the power of t minus 4 all over 0.681818.5. So I of t gives me 2.727 plus 1.273 e, and 1 divided by 0.68181885, that's minus 1.4667 times t minus 4, and that's your final answer for when t is greater than or equal to 4. Now the second part asks to find the current for when t is 2 and then when t is 5. So when t is 2, we can use this formula. So I2 equals 4 minus 4 e minus 2 times 2. And let me see what that gives me. That gives me 3.9267 amps. And then when I is 5, we have to use this formula. So it's 2.727 plus 1.273 e minus 1.4667, 5 minus 4. And let me see what that gives me. Okay, I get 3.0206 amps. And those are your final answers.